Hello, and welcome to this talk on direction finding and passive geolocation. I'm Greg Hovigam from the MathWorks, where I lead product marketing for our signal processing, radar, communications, and RF product groups. Today, I want to walk you through how MATLAB and Simulink support the full passive direction finding and geolocation signal chain, from intercepting signals in a contested electromagnetic environment through direction finding and position estimation, all the way to maintain tracking. We'll cover modeling, simulation, and importantly, implementation, meaning how you'll take these algorithms from desktop prototyping all the way to FPGA and embedded deployment without manual recoding. It's a technical talk for a technical audience, and everything I demonstrate is available today. This is the breadth of what we support for radar and RF system design with MATLAB and Simulink. Antenna design, radiation pattern design, full antenna-to-bit simulation, interference mitigation, radar system design, targets and environmental modeling, coverage planning, and RF front-end modeling. I want to emphasize that this is an end-to-end capability. You're not stitching together disconnected tools from different vendors. The antenna model feeds the propagation model, which feeds the signal processing, which feeds the tracker. Everything shares data structures and coordinate frames. So for today's talk, I'll focus specifically on the passive ES and direction finding side, but know that the underlying platform handles the full active and passive RF chain. So here's the structure. We will follow the passive ES signal chain from left to right. First, signal environment modeling, like how do we generate realistic electromagnetic scenarios for both algorithm development and AI model training. The contested spectrum isn't getting simpler, so generating high-fidelity synthetic data is foundational to everything that follows. Then, signal detection and characterization, intercepting signals in dense, congested spectrum and identifying what they are. Direction finding, given an intercepted signal, where is it coming from? We'll cover DOA, TOA, TDOA, and TSOA estimation. Then we'll validate with RF hardware, so you know that this isn't just theoretical. Emitter geolocation, where we combine multiple measurements into an accurate position fix, including GDOP analysis for optimizing sensor placement before deployment, and tracking, turning noisy intermittent detections into track custody. I'll close with implementation, taking algorithms from MATLAB to FPGA and embedded processors, and then our generative AI integration story. Along the way, I'll point to specific MATLAB examples that you can run today. The signal environment is dense and contested, and the RF spectrum is only getting more congested. This slide shows our current data synthesis capabilities for dynamic scenarios. We support monostatic and bistatic radar configurations, passive receivers and signals of opportunity, monostatic and bistatic clutter, polarimetric radar, and full multistatic networks. The key point is breadth. You can synthesize IQ data for any of these configurations. Passive receivers intercepting signals of opportunity are directly relevant to geolocation. You define your scenario, platforms, emitters, receivers, all moving in 3D space. And the framework generates time-tagged IQ data or detection level measurements at each receiver. This feeds your downstream detection, classification, and geolocation algorithms with realistic data. How much simulation fidelity do I need? It depends on what you're validating. We offer 3 levels shown on these axes. Power level at the bottom left, which is fast, statistical, thousands of Monte Carlo iterations, your link budget tool, your GDOP calculator, your coverage planner. Measurement level in the middle incorporates the radar equation, propagation losses, and noise to produce realistic detections. You get SNR and detection ranges without computing full waveforms. This is where you design your tracker. And signal level at the top right. Full IQ physics at every receiver. It's computationally expensive, but necessary for algorithm development and hardware-in-the-loop testing. The right approach uses all 3. power level for architecture trades, measurement level for system performance, signal level for algorithm validation. They're integrated in the same scenario definition, so you move between fidelity levels without rebuilding anything. Run your coverage analysis in a planning meeting, then drill into signal level at your desk for the geometry that you're interested in. LPI radar is relevant because adversaries deploy techniques to defeat systems performing geolocation. On the left, the characteristics that make a radar low probability of intercept, such as low sideband antennas, irregular scan patterns, low power with high duty cycle, LPI waveforms, frequency agility, and high processing gain. On the right, what simulation lets you do about it is parametrically evaluate intercept probability as a function of your receiver sensitivity, bandwidth, integration time, range, and geometry. A critical insight is that LPI status depends on the receiver. A radar might be LPI against one ES receiver, but not another with different characteristics. Rather than discovering your ES receiver has a detection gap against a specific LPI waveform during an operational test, when it's too late to redesign, you discover it in simulation early enough to modify your receiver parameters or processing chain. Beyond individual signals, you need to model the full bistatic scenario. For the three configurations on the top, cooperative, where you own both the transmitter and receiver as a dedicated pair of assets. Non-cooperative, where you exploit signals of opportunity from broadcast towers, cellular base stations, or other emitters that you don't control. And multistatic, for multiple passive receivers forming a distributed sensing aperture. And two configurations at the bottom, mechanical and electronic scan models. Full dynamic scenarios with platforms moving in 3D. For this talk, the non-cooperative and multistatic configurations matter the most. Your receivers passively intercept signals from transmitters that you don't control, and you geolocate by fusing measurements across your distributed receiver network. All of this runs at both measurement level and full signal level fidelity. This is a complete end-to-end example of non-cooperative bistatic radar IQ simulation and processing. The workflow runs left to right. Set up a passive bistatic scenario with two unknown transmitters and one receiver, one target. Simulate the raw IQ signal at the passive receiver. Then process, de-interleave the received signals, estimate the pulse repetition interval, PRI, identify the reference waveform, and estimate the direct path azimuth angle. Finally, perform bistatic range Doppler processing, direct path mitigation, beamforming, CFAR detection, and parameter estimation. This is a published documentation example that you can run in MATLAB today. The same processing pipeline applies to passive radar exploiting GNSS or broadcast signals for alternative positioning. I'll note that the IQ interface here is hardware agnostic. So whether your front end is a Keysight, National Instruments, or custom DERFM, the MATLAB reads the same IQ format. Now, once a signal arrives at your receiver, how do you characterize it? So let's move on to signal detection and characterization. Given signals in the environment, how does a receiver intercept, detect, and characterize them? This is the first step of the signal chain. We need to identify what's in the spectrum and determine its parameters before we can locate it. AI and machine learning for signal classification appears in every issue of the Journal of Electronic Defense, every DoD EW modernization program, and every industry survey. This is where AI and machine learning become essential for modern ES systems. Traditional signal classification relies on parameter matching against emitter databases like EWIR. You look up the PRI, the frequency, and the pulse width to identify the radar. But modern emitters are agile. They change parameters adaptively, use low probability of interest waveforms, and operate in dense spectral environments where de-interleaving alone is a tough problem. The workflow at the top shows our full AI pipeline. Access and acquire signals, pre-process and label them, transform signals and extract features, train the AI models, and deploy to embedded systems. 2 interactive apps are highlighted. Signal Labeler provides signal exploration and labeling. Labeling being the critical workflow for building training datasets from captured or simulated IQ data. You can label in time, frequency, or time-frequency domains. Signal Analyzer gives you multi-domain visualization simultaneously across all representations. Combined with synthetic data generation, you create millions of labeled training examples across parametric variations of emitter characteristics. You don't need to collect it all from the field, and you don't need to wait for a signal you've never intercepted before. Train the classifiers for automated modulation recognition or specific emitter identification. Then deploy to your embedded target, whether that's an FPGA for real-time throughput or a GPU for batch processing through code generation. A critical use case for the waveform simulations I just showed you is creating datasets to train AI models. On the left, generative synthetic data using adversarial networks to go beyond classical waveform codes and generate novel signal variations of your system hasn't been seen before. In the center, physics-based LPI radar signal generation, NLFM, Lejeune-coded, and other waveform types that your ES system needs to detect and classify. On the right, dataset augmentation, injecting synthetic targets and interference into recorded datasets to expand training diversity. This solves the fundamental labeled data problem. You generate unlimited training examples for signals you've never intercepted, including hypothetical future threats at any SNR with realistic interference conditions. This example shows automated labeling and classification of time-frequency regions in spectrograms. The top panel is a short-time Fourier transform of a captured 2.4 GHz spectrum overlapping Bluetooth, BLE, and WLAN signals sharing the same band. Below, the clustering results of an AI model has automatically segmented and classified each signal by type. BLE at 1 MHz, BLE at 2 MHz, Bluetooth Classic, WLAN BGN, WLAN N, and all identified without any human intervention. This is the automated spectrum awareness that modern ES systems need. So you build the classifier from labeled spectrograms, either from manually tagging or simulation, and then deploy them for real-time inference. We're also leveraging vision-based AI models for automated time-frequency segmentation. Approaches that originated in computer vision translate directly to spectrogram analysis. This is a more targeted AI application for a training model to estimate radar parameters from noisy observations without knowledge of the transmitter. This uses the 3.5 GHz CBRS band, where government radar coexists with commercial users since 2017. The dataset is 800 simulated waveforms, rectangular pulse and linear FM, with pulse widths down to half a microsecond, making detection extremely challenging at low SNR. The technique is to compute spectrograms, apply max pooling over the frequency to enhance radar pulses that are shorter than the analysis window. Then use a YOLOX detection network to find individual pulses and estimate their parameters, bandwidth, pulse width, modulation. The results table shows estimated versus ground truth bandwidth within about 10%. This is a published example with data from the NIST Public Data Repository, generated using Phased Array System Toolbox. And the reason this matters operationally is if your ES system can estimate waveform parameters without a matched filter, you can characterize emitters you've never seen before, which is increasingly the scenario in contested environments. Okay, direction finding. Given an intercepted signal, where is it coming from? This section covers DOA, TOA, TDOA, and TSOA estimation. Critically, what I'll show you here has been validated with live RF hardware, not just simulation. And the same code that processes simulated data is used to process real over-the-air signals without modification. Here's the taxonomy of direction-finding techniques organized by requirements. Under line of sight, 3 options. Direction of arrival requires an antenna array, measures phase differences across elements to determine the bearing. Single platform, but gives you angle only, not range. Time of arrival requires time synchronization across all sources and receivers and gives you range directly, but requires transmitter cooperation, which makes it kind of impractical for passive ES. TDOA, time difference of arrival, is synchronization across receivers only, independent of the transmitter. You measure arrival time differences between receiver pairs using GPS-disciplined oscillators. This is the most practical technique for passive geolocation because you need zero cooperation from the emitter. And when line of sight is unavailable, time sum of arrival, bistatic range, uses the total path length through a target to define an ellipsoid. This works for passive radar using illuminators of opportunity, and each has different hardware requirements. The right choice depends on the platform and the synchronization capabilities. For DOA estimation specifically, we implement 6 algorithms, each shown here with its spatial spectrum output from the same array. Monopulse, classic sum and difference beams. It's fast, it's low computationally cost, most common for airborne radar warning receivers. Music, multiple signal classification, subspace-based, super resolution even at low SNR, but requires knowing the number of sources. IAA, iterative adaptive approach, is wideband compatible, no eigen decomposition. Beam scan, conventional beamforming swept over angle. It's robust, but resolution limited by the aperture. MVDR, minimum variance distortionless response, is an adaptive beamforming, good resolution without needing source count. And DeepNet, a learned DOA estimator trained on synthetic array data. It provides robustness at low SNR where classical methods degrade. All 6 use the same array object in phased array system toolbox. So you benchmark them all against your scenario in a few lines of code to determine which meets your accuracy requirements for your platform constraints. The first question a skeptical engineer asks is, does this actually work with real signals? This slide answers the question. On the left, the physical setup of a USRP X310 software-defined radio with twin RX daughter boards forms a 2-channel coherent receiver and a separate USRP transmitting a known signal. On the right, the documentation example showing the music algorithm estimating the direction of arrival from live captured IQ data. This is new in R 2026A, and the workflow implication of this prototype and simulation with full control over the scenario, then validate with real RF to confirm your assumptions, hold it in the physical world. Same MATLAB code, same functions, same calibration objects, no rewriting between simulation and hardware validation. The array calibration data you measure on your bench feeds directly into the same objects your simulation uses. So your sim matches your hardware by construction. This is a seamless transition that eliminates re-implementation risk. Time of arrival estimation. The principle is straightforward. Signal propagation time is proportional to range between emitter and receiver. We estimate TOA by processing the channel impulse response. 2 approaches shown in the lower panels. FFT-based spectrum estimation gives a coarse TOA estimate, while music-based processing gives sharper resolution for closely spaced multipath components. The geometric interpretation on top, 1 TOA measurement from a single receiver, defines a circle of possible emitter locations. You need multiple receivers to resolve position. TOA is the foundation for both TDOA differencing and multi-static geolocation methods coming up. Applications include passive source localization for electronic support measures and any scenario where you have time synchronized receivers. TDOA is the workhorse of passive geolocation and the most relevant technique for this audience. The principle, the difference in arrival times between two receivers, defines a hyperboloid of possible emitter locations. On the left, a single TDOA measurement. The emitter lies somewhere on that hyperbola. On the right, the family of hyperbolas for different time difference values between a receiver pair labeled in microseconds. The critical advantage is you don't need to know when the signal was transmitted. You only need relative timing between your receivers, achievable with GPS-disciplined oscillators. This makes TDOA fully passive and independent of the emitter. To localize, you intersect hyperbolas from multiple receiver pairs. 2 pairs gives you 2D, 3 gives you 3D, and accuracy depends heavily on receiver geometry, which brings us up to GDOP shortly. TSOA, time sum of arrival, also called bistatic range, is increasingly relevant for passive radar. The concept, the sum of transmitter to target and target to receiver distances, defines an ellipsoid of possible target locations. If you know the transmitter position, a broadcast tower, GPS satellite, and your own receiver position, one TSOA measurement constrains the target to an ellipse. Multiple measurements from different geometries give you a position fix. The equation at the bottom shows the relationship explicitly. This is the foundation of passive coherent location systems that exploit things like FM radio, digital television, cellular, or GNSS signals as illuminators. No dedicated transmitter is required. It's completely covert for reception, and when GPS is denied for navigation, these same signals of opportunity provide alternative positioning. Okay, emitter geolocation. A single bearing is not a position. How do we combine multiple measurements from multiple platforms, multiple times, or multiple techniques into an accurate geolocation? This section covers multi-platform localization and the critical role of geometric dilution of precision and cooperative methods. This is one of the most important concepts for mission planners. On the left, TDOA multilateration. These are hyperbola intersections localizing the emitter. On the right, the GDOP heat map. Dark blue is low uncertainty, it's good for accuracy. Yellow and orange is high uncertainty, which is potentially kilometers of error. Notice that accuracy degrades along the baseline between the receivers and improves perpendicular to it. The practical implication is, before you deploy sensors, simulate your GDOP. Where can you geolocate accurately and where can you not? Collection geometry is the dominant error source in passive geolocation. More important than timing accuracy, more important than algorithm selection. The best algorithm can't overcome poor geometry. You need a minimum of 3 receivers to localize in 2D, and in MATLAB you can compute these maps, optimize sensor placement for minimum uncertainty across your target area, and brief planners on where the constellation performs and where it doesn't. This is a mission planning tool as much as an algorithm development tool. These are 4 primary geolocation methods we've implemented. AOA triangulation, which is multiple bearing lines from different sensors. Where they intersect is your emitter. But notice the ghost intersections in black. With multiple emitters and sensors, you get false intersections. Tracking resolves the ambiguity. TOA multilateration, range circles from multiple synchronized anchors intersecting at the target. TDOA multilateration, hyperbola intersections from receiver pairs, no transmitter cooperation needed, and it's the most practical for passive systems. And hybrid TSOA plus AOA is combining bistatic range ellipses with angle measurements in 3D, which is powerful for passive radar with directional receivers. Plus other hybrid techniques like AOA combined with TDOA that fuse different measurement types into improve accuracy and resolve ambiguities. The right method depends on your operational constraints, the available sensors, the synchronization capability, and collection geometry. Tracking. We know raw geolocation measurements are noisy, intermittent, and contaminated with ghost detections from incorrect line-of-bearing associations. Tracking is what transforms a cloud of noisy measurements into maintained custody of the target. Knowing where an emitter is, where it's heading, and correctly associating measurements to the same source over time. This is where data becomes smart. This is the before and after that motivates tracking. On the left panel, the raw angle-only detections from passive scanning sensors. There is ghost intersections everywhere, missed targets, no association between measurements. It's not usable for decision-making. On the right panel, after tracking, ghosts are eliminated, true emitters are maintained with smooth trajectory estimates, and that leads you to actionable information. The tracker uses Kalman filtering to predict target state, data association to match new measurements to existing tracks, and track management to initiate, maintain, and drop tracks. For angle-only tracking, the common case in passive ES is that you need to maneuver the platform or do multi-sensor fusion to achieve range observability. A single stationary sensor measuring angle only cannot determine range. It's just fundamental geometry. This is a published documentation example in Sensor Fusion and Tracking Toolbox that you can run today. What if you have a single passive sensor with no cooperative partners? A submarine maintaining MCON, a stealth aircraft, anything that cannot emit and has no data links. The answer is passive ranging through platform maneuvering. By changing your position over time while taking bearing measurements, you generate the angular diversity needed to triangulate range. The diagram shows an observer maneuvering, taking bearings at each point. Below, the resulting track estimation converging on the target position. The critical insight is that observability requires sufficient cross-range maneuvering. A straight line course toward or away from the target gives you essentially zero range information. In MATLAB, you simulate different maneuver profiles to determine the minimum geometry your platform needs for convergence, which is a critical part of planning collection flight profiles before mission execution. The trade-off you're always managing is more aggressive maneuvering because it gives you faster convergence, but it increases your own observability. Simulation lets you find the minimum maneuver that achieves your accuracy requirement. Everything I've shown so far runs in MATLAB on your desktop, but these algorithms need to execute on FPGA fabric and embedded processors in fielded systems. This is where the simulation to deployment story matters the most. On the left, HDL Coder generates synthesizable Verilog and VHDL directly from your MATLAB or Simulink algorithm. No manual HDL coding. The two examples at the bottom demonstrate FPGA-based monopulse direction finding. Part 1 covers algorithm design and fixed point conversion in MATLAB. Part 2 generates the HDL and shows the FPGA implementation results. The same algorithm you prototyped and validated in Phased Array System Toolbox is now running in hardware. On the right, C and C++ code generation using MATLAB Coder and Embedded Coder for embedded processors and DSPs. The specific example shown is a multi-object tracker deployed to the ARM Cortex processor on a Texas Instruments millimeter wave radar evaluation module. The value proposition is significant. Eliminate manual recoding that introduces bugs. Eliminate the transition errors that inevitably occur when one team designs algorithms in MATLAB and a different team hand codes VHDL or C for hardware. The algorithm you validated in simulation is byte for byte the algorithm you deploy, and you can run bit-true verification in simulation against the generated code before committing to hardware. That catches fixed point issues and timing violations before they become expensive board spins. Let me bring it all together. This diagram shows the full radar and EMSO system architecture with MathWorks toolboxes mapped to each functional stage. On the left, environment modeling with mapping toolbox and our scenario framework, terrain, propagation, platform kinematics. The antenna and RF front end with antenna toolbox, RF toolbox, and RF block set. Signal processing with phased array system toolbox, communications toolbox, and radar toolbox. This is where your DF algorithms live. Data processing with sensor fusion and tracking toolbox for tracking and fusion, supported by statistics and machine learning toolbox, and deep learning toolbox for the AI-driven classification we discussed. And resource management and controls, closing the loop. So these are 4 key takeaways, and these are what I want you to remember for tomorrow morning. 1, many simulation tools address each stage of the ES signal chain to detect, characterize, locate, track, and decide. And we have validated these with live RF hardware, not just simulation. 2, AI and machine learning signal classification is enabled by synthetic training data that you generate in simulation, solving the data scarcity problem. 3, multi-platform scenarios for distributed sensing architectures. Cognitive EW demands simulation for pre-training adaptive systems, and you can't generate enough operational data alone. 4, from algorithm to fielded system through automated code generation to FPGA and embedded targets. No manual reimplementation. That concludes our talk on direction finding and geolocation. You can learn more about MathWorks at mathworks.com and follow us on social media. Thank you.